Torque on a current loop. Electric motor is a loop of wire, usually rectangular and free, to pivot about a vertical axis, is placed in a magnetic field. When these wires are placed in a magnetic field, current is produced. Now we want to figure out how this is done, and those constitute electric motors. So motion of a current carrying loop in a B field. As the current is the current moves through it, the north and the south pole will actually act on, will have different fields that act on it. The field will go up one way and the field will go down the other way. And that introduces a rotation. And this rotation introduces more rotation, and inertia and rotation together will bring out something that's called torque. So the net force and the net torque on the loop in an external magnetic field will be given by this. So the net force will be 0. However, the net torque will be given by BIAB sine of theta, where A and B are the length and the width of the loop that's carrying the current. A is the area, and B is the strength of the external magnetic field. So for a loop that has n turns, the net torque on each loop will be BIA, where I is the current that's carried, BIAB sine theta. The torque on the whole coil will be NIAB sine theta, where A is the loop, area of the loop, and N is the perpendicular to the loop. A galvanometer is an electromechanical instrument for detecting and measuring electrical current. So as the current moves from the positive to the negative through a coil to the magnetic field generated by the coil. This field is interacted by a permanent magnet that's present inside the galvanometer, and it forces the coil to twist, moving the pointer, and as the current increases or decreases, the pointer will move more or less, telling you how much current passed through in those coils. So now let's do an example. Show that there is 0 net magnetic force on the pivoted coil in the galvanometer of the figure below. B, show that there is a net torque. C, the net torque is in the correct direction to the swing of the pointer in the plane of the page. And D, determine which direction of the current in the coil must go to swing the pointer towards the right. There are a few assumptions. Assume that the magnetic field is radial and has uniform magnitude and space between the magnetic pole faces and iron core, and then the field is 0 in the vicinity of the two sides of the coil that cross over the iron core. So let's draw a picture. Assume that this is the north pole. This is the core. This is where the coils are being wrapped. This is field going out. This is field going into the paper. And then these fields are actually connected to each other. Okay? And then there is a south pole here. So the south pole goes this way. Okay? Here's where the pointer is, and here's where the galvanometer scale is. Okay? So this is where the pointer acts. Okay, so now that we have our picture, we can figure out lots of things once we have that figured. So we know that the field that goes from the north pole to the south pole will look something like this. As it goes, so it'll go sort of like this because of the shape. It will sort of point in, and this field will sort of look like this, and it will point towards the south pole. Okay? That's one thing we know. We can choose I towards north pole, flowing into the page like this, and I choose I towards the South Pole to be flowing out of the page. Okay? So this would be represented by these dots here. Okay? So towards the north, it will be represented by this. Towards the south, it will be represented by this. Okay, so now let's do this problem. Number 8. We have to prove that the net FB on the galvanometer equals to 0. How do I do that? Well, the B vectors are the same, and L are equal and opposite. This implies if I use N I L over B, because my field vectors are equal and opposite, that means that my net force acting should absolutely be equals to 0. Okay? Now, part B. What is my net torque? Okay? Technically, if I have my net B equals to 0, and I know that torque equals R times F, right? So that means a delta sigma T should also be 0? The answer is no, and the reason why the answer is no is because R is the action, the line of action, and those are different for this side and that side. So that means that delta torque is not equals to 0. Okay? Number C. It says torque is in the direction of the swing to the pointer of the plate. So the forces make the pointer rotate counterclockwise, and that is in the plane of the page. So the forces will make the pointer rotate counterclockwise in the plane. So that means it is going to go counterclockwise. Part D. Determine the direction of the current the coil must go to swing the pointer to the right. Okay, so this means that the forces that we chose will make the pointer go anti-clockwise. So our choice, in order to make it go clockwise, has to be opposite to what I chose. Which means that, in fact, it should have been that I towards the North Pole should have been flowing out of the page, and I towards the South Pole should have been pointing into the page. So my choice was incorrect. In order for this pointer to go clockwise, I have to choose, re-choose I to point out of the page, or when it's going towards the North Pole, and re-choose I into the page when it's going towards the South Pole.